Yeah, no, it'd be a good job for a university student, but yeah, whatever. Okay, so volumes of solids by plane slices. So what I'm asking you to think about is a cylinder is comprised of, and this is the calculus way of thinking, not. I know these are very cylinder-like, but a cylinder is just a bunch of discs, a bunch of really thin discs. A cylinder is just an infinite number of circles stacked on top of each other. Not this thick of a slice of paper. So to find the volume of a cylinder, truthfully, instead of grade 9 where we gave you the formula pi r squared h, what we should have made you do, if we were being really neat and developmentally according to how we develop the volume of the cylinder, we would need to create an infinite number of circles on pieces of paper and then stack them. Because that's actually where the formula comes from. Now, probably way back when we first discovered the idea of volume and capacity, invented, created, whatever. Somebody could write me a paper on that. We probably didn't worry too much about that, but as soon as we started to look at the ideas of calculus, we recognized that what we're really doing is just finding the area of a circle, and then we're multiplying it by the number of circles we needed to create volume. Yeah, can you see that link now back to integration? So each circle has some radius r and some height h, and the formula for the volume of a circle is pi r squared h. But really what we're doing here is saying take the area of a circle, and h is kind of like the number of circles. Same thing here on its side. But notice this one's being rotated around, they're being rotated around different axes. So I'm starting to get you used to the idea of you need to look at which way it's being sliced. This one's being rotated around the y-axis. This one's being rotated around the x-axis. Yeah? So what we're really talking about here is the y-coordinate, is the radius. And then the height is what? Is the x-coordinate, so it's the dx going to come in. Okay, height is going to be the x-coordinate. And then over here on this blue circle, or the one that I drew on, the radius is going to be the x-coordinate, and the height is going to be the y-coordinate. Yeah? So which way do you orientate? Orient. Which way do you orient your cylinder? Okay. Consider a bounded region and rotating that region around the x-axis. Take a slice and consider its volume. Okay, so what we're saying here is this. I've got my Donut King coffee cup turned on its side, and no, I'm not going to turn it on its side because it's full still. But I can graph it, and it looks like this. And it's got this shape, and I want to ask you what the volume of that coffee cup, you have to visualize it being spun. Yes, I know I can't draw, I failed art. Probably the only teacher in the world to ever do so. There we go. So we're going to integrate. We're going to find the area under this curve, and then we're going to spin it around the axis. And when you take that area and you spin it around the axis, you have to visualize that. It creates a volume. It creates the coffee goodness that Mr. Epp appreciates. Right? It's the coffee inside the cup I'm talking about. You take the equation of the inside of this. Just a second. Okay, so you take that and you rotate it around the axis really fast, and it creates a volume state. Yes. No. Yes, but no. So what we're going to do is we're going to take the antiderivative. So my mug starts at 0, and it goes out to some coordinate, I don't know. You know what? We shouldn't start at 0. We'll start at some coordinate a, f of a. And it goes out to some coordinate b, f of b. So to find the volume of this coffee cup on its side, we're going to find the area from A to B of pi r squared h what's r? It's the y coordinates, kids. What's h? Oh, we've already done it. Yeah, but it is a cylinder because each of these little mini slices are cylinders. Yeah. Yeah, that's fine. Doesn't matter. It's all the same in calculus. Because the y coordinate is, so all we're doing is adding up a bunch of circles. That's what this is saying. To add up a bunch of circles. And when you stack up a bunch of circles, if all the circles are the same radius, then it's a cylinder. If all the circles get smaller and smaller and smaller until they reach a point, it's a cone. If it goes out on a V-like shape, it's Mr. Epp's Donut King coffee mug. That f of x formula controls the shape that you're finding the volume of. It actually doesn't matter if it's a cylinder. If I hold the radius constant, it creates a cylinder. But if I hold the radius in a decreasing, it creates a cone. It creates a cone. If I create an increasing shape, it creates a mug of coffee. No. Say that a little louder. It's called a truncated cone. When you take a shape and you flip it and you cut part of it off, it creates something called a frustrum, but you don't want to know that. You can't. That's how it works. All we need to do is say this is what because this is the height. A to B says take all the slices, add them up, and the area of each slice is. So add up an infinite. Just maybe we need. So it depends on the shape. I have to define a shape. Okay, so this one could be the function. This could be the function y equals x plus 2. So when I do this question, maybe it starts at 0 and it goes up to 4, because I'm going to get a ruler out and measure my coffee cup. H is the integral. H is the integral. Mr. Epp, your coffee cup is... You don't need an H. I forgot. Your H is your integral. 15 centimeters. So if I wanted to find the volume of this cone, I would integrate from 0 to 15 of pi times, we said y plus 2. We could figure it out actually if you'd like. No, I'm not going to. Sorry, x plus 2. X plus 2 squared dx. And we would find that volume. And that would give you the volume of my coffee cup. Yes. Pi r squared. Pi r squared. I'm just taking the radius of each of the circles and adding them up. Yes, I'm taking the area formula and I'm stacking the areas. Which is actually how they teach it in grade 8 now. In grade 8, they don't give all the volume formulas. They say the bottom of the shape looks like this. It has some area A, and then we stack wafers of it that all have the same area A. The volume of that shape is A times H. So for calculus, it's just the antiderivative of A dx. And this, we'll call this x the amount it stacks up. Add up all the stacks. Yeah, now I'm using height. All this means is to add up. That's all it means. Okay? So if you flip back here and we look at this, where is it? It's just the adding of, all it does is say, add a whole bunch of circles together. And when you add up a whole bunch of circles, you get a volume. Here, add this circle together with this circle with this circle. You've got nothing with volume, but when you combine them together, they create volume. Probably nobody's ever asked you to think this way, have you? So take the volume of each slice. What do you get? What do you get? Okay, so the volume formula that I want you to use is this. V equals the area antiderivative between A of B. Take the pi out front because it gets in the way. F of x dx. That's one way of doing it. The other way of doing it sorry, yeah, good call. So that's doing it with around the x-axis. If we do it around the y-axis, it looks like that. Oh, forgot my square. Well, yeah, sure. You want to use, yeah, you know what? That's a good call. Because this one's rotating this way around the axis, and then this one's rotating this way around the axis. But it's still pi r squared. You have to just decide which axis you're going around, where are you starting, where are you stopping, what's the formula. So the region bounded by the curve y equals the square root of x, and the x-axis over the interval 1 to 4 is rotated about the x-axis to generate a solid. Because we're not making boring Donut King coffee cups anymore. Sorry, Donut King. We're making exciting Donut King coffee cups. So find the volume of the solid. So we're going to draw the curve. We're going to go from 1 to 4. 1, 4. We're going to spin it. And can you see the exciting mug that we're making? Or solid billet aluminum. We're making chrome hubcap lug nuts. We're machining them down in on the CNC machine. Sorry. That's for the trades kids. Hey? Making solid chrome. Yeah. Yay, calculus! Anyways, so we're going to do the integral from 1 to 4 of the square, pi square root of x squared dx. Bless you. What do you got? Pi. Mr. F, I'm going to simplify that. Good answer. So 8 pi minus a half pi. 7.5 pi. 4 squared is 16 divided by 2 is 8. Yeah, 8 pi. 7.5 pi. A mixed irrational number. No. Scare your grade 8s. Mixed irrational numbers. That's a mixed fraction with an irrational number attached. 7.5 pi. Do you prefer 15 pi over 2? You don't care? Same thing. Okay, flip page. Okay, so this needs to be over here. I don't know what happened. Find the volume of the solid generated by revolving the region bounded by the lines and the curves about the x-axis. So y equals x squared. Looks like this. And we're going to bound it by the curve, x equals 2, and the curve, y equals 0. So I want, now I'm making like a little shield point at the front of the shield, or a, I don't know. What else? When you spin it, what else would this be? A top, yes. Half of a top for a grade 8. Okay, so you got to keep them interested. So we're going to find the area of that curve, and then we're going to volumize it. So we're going to find the antiderivative from 0 to 2 of the function pi x squared dx. Pardon me? But I always put the pi out front because it's a constant. Get it out of the way. It doesn't get you into trouble then. So the antiderivative of x to the 4th is x to the 5 over 5. 0 to 2. Put a pi there. 2 to the 5. 2 times 2 is 4. 2 times 2 is 8. Then pi. 32 fifths. 32 pi over 5. And then, ooh, this is exciting. Secant x. Secant is 1 over cos. So cos looks like this. So secant looks like this. And we're going from pi over 3 to pi over 4 to pi over 3. Ooh, that's exciting. Like that. What? I'm guesstimating. Because that's pi over 2. So pi over 4 is going to be halfway. Would I expect you to draw? No, I would just do it. All you would see on my page is this. Bang, bang. Oops, did I square it? Right. So the antiderivative of secant squared. Mr. Upham. Secant, no.
Rory Pritchard, you have a message in the upper campus office. Rory Pritchard, message in the upper campus office. Thank you.
Oh, no. Yeah, pi over 3 is bigger than pi over 4. What? Secant squared isn't tan. Oh yeah! Oh, shut up. Shut up! You guys are awesome. Yay! Yay! That's so cool. Just a sec, I'm having a moment. You're an idiot, Mr. F. Okay, pi. Yeah, and pi over 4 is smaller than pi over 3. You're dumb. Anyways. Okay, so tan of pi over 3. Oh, tan of pi over 3, root 3 over 1. So pi root 3 over 1 minus 1 over 1. So that's the volume. Stupid special triangles. Who needs those things anyways? Are we good? We see how this is going? Do we want to do one more? Oh, let's go about the y-axis. This will be fun. No? Okay, take this example and put an arrow over there. Okay, so y equals 1 minus x squared. You look at it and you go, but it says rotating it around the y-axis. So the first thing we need to do is make this x equals. So y minus 1 equals x squared. Plus or minus the square root of y minus 1. Yes? Oui? Ouais? Okay, so we graph that. This is a parabola on its side. Oh yeah, sorry. There. I just flip things around in order when I'm bending it. Okay. So we got to graph this. And I don't want to anymore. I don't want to anymore. Ugh. We got to graph this. X equals plus or minus. I'll just use. I'm going to cheat. We can eventually. Equation. Where do I want to put it? Is it parametric? No, it's not polar. It's explicit. No, it isn't. Why am I doing this? Okay, I just got to do this. I'm just going to do it the way I want to do it. I'm just going to graph this and then recognize that I have to use that equation. Mr. Up, that's a parabola moved up one opening down. There. I'm like, why am I wasting my time? That's a parabola opening down, moved up one. The original equation. Okay, so draw your curves for boundaries. So x equals 0, y equals 0. So what I'm looking for you to do is to find this pink area and then spin it. This is making a nose cone for a missile that we're shooting at somebody. I know. Mr. F, you're way too violent. Now, the nice thing you have to recognize is you don't have to use the plus or the minus. Because all we're doing is going from here out to here. That's the root of 1 minus y. It's not the minus root. That's on the other side. It doesn't matter. Because when we rotate it around, it does both sides, yeah? So, pi, so we need to know our y coordinates. The y coordinate there is 0. What's the y coordinate up here? 1. So we're going to integrate from 0 to 1 of f of y squared dy. And we'll put a pi out in front of that. So find that volume. Half pi. I mean, yeah? Pardon me? 1 pi minus half pi, half a pi? Yeah, okay, let's do the one on the right and then we'll stop. So, we're going to do the same thing, but we're going to do x equals 3y squared. We're going to do it from y equals... Okay, this one's easier because it's already set up for you. Yeah? Do we see that it's already set up for us? So do we even need to draw a picture? No, we don't. Anti-derivative negative 1 to 1. Oh, just a sec. Maybe we should, just in case it's doing something silly. X equals 3y squared. Mr. Epp, that's a parabola. X equals y squared. What does that look like? Doesn't it look like this? From y equals negative 1. Oh. 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 No. Well, look. Well, I don't know. Yeah, I think we're talking about this area in here. Now, does it say? I'm questioning myself right now. I'm thinking because I'd say the answer is 0 because you have equal amounts above and below. But I don't think when we want to use the word volume, I don't think we were going to say it's 0. So what I would do is just integrate between 0 and 1, and then... Yeah, it is. Yeah. That's my... Yeah, I think that's the way we want to attack that. Which axis are we going around? Oh, that's why. Oh, that's why. I'm an idiot. No, yeah, we're going around the y-axis. Yeah, no, that makes sense then. Yeah, you do want to go from negative 1 to 1 then. I was going around the x-axis. That's why. Okay, who was saying it was 0? Besides me. I was like, oh crap, I'm going around the x-axis. It's you got to go around the y-axis. What? No. It's not. No. Because we're taking this billet piece and spinning it around and making like a Like making the end of a bottle. That's not zero. So this isn't zero either. No. Yeah, right. Okay, so are we clear that this is what we have to do? Do you want me to do it, or that's okay? Okay, we'll stop here.